Assalamu alaikum. So using MATLAB code we have to solve this problem. That means you have a message signal with AWGN type noise. That means you have a noisy signal of SNR minus 10 decibel. So now you have to detect that signal. So using auto correlation you have to just get an idea of that uh, message signal and find the frequency of that signal. Okay, so let's start. So we have divided this into three steps. As step 1, I have to create the message signal. First I will create the sinusoid signal, then I will work with other types of signal. Okay, now at step 2, I have to make a noise signal and add that signal noise signal to the input signal. That means I will make a noisy signal here, and at the end of this video I will detect the message signal from that noisy signal, and at later we will do a frequency analysis to find the frequency of that message signal. Okay, so let's start. So let's say that I want to make a sinusoid signal, and to do this I choose time period is 2 millisecond and the frequency is 500 hertz, and by this codes I simply make the sinusoidal function. Okay, so now let me run this portion here, and then let's come here. So if I run this portion or run this cell, I get a signal like this. So what is this actually? First of all, this line gives you the power of your input signal, and the power is 6000. Okay, let's forget that. Now what this function is doing, you are using a built-in xcore function, right? So let's see what xcore is doing. So xcore, so if you feed two signals in this xcore built-in function, let's say one is x1 and another is x2, then it will give you the cross correlation function. But we don't want this cross correlation function. In this video we want the auto correlation function, and if you pass only one parameter, then you will get the auto correlation function for x, and also you will get the L index for this input. Okay, so you get the auto correlation function of x, and then if you plot this auto correlation function after normalizing it, then you will get a signal like this. So this is the ACF of the sine signal. So you have to remember that this is the ACF of the sine signal because it will be needed later. Okay, so remember this shape. This is the ACF of sine signal. Okay, now let's go to step 2. So add noise of specific SNR. Okay, so now we will add some noise to our input signal. So what is this AWGN? So if it is a built-in MATLAB function. So if I right click here and open AWGN, then it will show me the function here, and at the beginning you have some guidelines how to use this function, and you have to just read this portion. Okay, so you will read it later. Let me explain what AWGN is doing. So AWGN, okay, let me first tell you about what is AWGN type noise. Okay, so AWGN means additive, and W is for white, G is for Gaussian, and N is for noise. So it's a noise, it's an additive white Gaussian noise. So how this noise works, let's say you have a input x, and the noise works additively. I mean, this noise adds with this input signal and you get the noisy signal. So to make this noisy signal, I have to use this awgn built-in function. So awgn is the built-in function. So first you have to put x here, then you have to put the value of snr, and then here you have to write measured, then here you have to write measured. And if you do this, then you will get the noisy signal. Noisy signal means this signal has the input and also the awgn type noise. So simply write it noise. So you have the input and noise added together, and this makes the noisy signal. Okay, so let me go to the code. So this is my input x, and the value of this snr is -10, and I have written here measured. So here is a guideline that if you write measure, then what will it do? So when you use measure, then awgn will measure the signal power before adding noise. I mean that if you use measure, then first it will measure the measure the power of this input signal, and then it will add the noise with that signal. Okay, and this is a simple line. I just try to find the power of noise, but it's not the main part. The main part is I have to now I have plot the noisy signal. So if I plot this, then you will see that this is my noisy signal, and sinusoidal signal is not visible here. Okay, because my snr is only -10, it's so poor. But if I increase this snr, let's say it's 10, then see the sinusoidal signals starts appearing. If I improve this snr to 100, that means it's a good signal and noise is so less. So if I run this code, you will see that it's a clean signal, a little noise here. But in this video we will work with the worst condition, -10, and if I run this cell, only this part, so this is the noise. So I don't have any idea what is the message signal. Okay, so now I have to this is my noisy signal, and let's say I don't know what is the message signal, what is the original signal. So now I have to detect, step 3, I have to detect the message signal from noisy signal. Okay, so let's see how can I do this. So first of all, I have to again make autocorrelation of noisy signal, and thus I can find the ACF of noisy signal, autocorrelation function of that noisy signal. And then I have normalized this noisy signal. That means I have bounded all the values from 0 to 1, and then I just plot the noisy signal, and let's see what happens. Okay, that's what I wanted. So I got a spike here, and this spike at 0 is for the noise. Okay, so this spike is for the noise, and this looks like delta. So this delta is only for the noise, but here you see the pattern. Is it familiar to you? Yes, this looks like the ACF of the message signal, right? Let me find the ACF. So this is a clean ACF input. The ACF of the input, I mean the autocorrelation function of the input, that means ACF of the sinusoidal signal. And this part looks also like this, and this part also looks like the ACF of the message signal. So by this you can get an idea that it's a sinusoidal signal by observing this shape. Now let's say you want to know the frequency of this this noisy signal. Okay, so we have to do an F50 here. It's the off topic. Just with this code I will try to find the frequencies of this noisy signal. So if I run this code, run this portion, now you see that I have frequencies. This x-axis I have the frequencies. So all the frequencies have a low weight or low power, but here I have only two frequencies which has the highest impact. So this is x is equal to 500 and this is x is equal to minus 500. This is x is equal to minus 500. So from here I can understand that the frequency of the message signal is 500, and let's see in my code. So the frequency was 500, our original frequency was 500, and after a long process, after doing F50, I understand that the frequency of this message signal is 500. You may wonder that why these two spikes are coming. One is minus 500, one is minus 500, and another is plus 500. Why these two spikes are coming? So let me tell you that. We can write sine, let's say sine omega t. I can write it as e to the power, okay, let me break this thing like this. E to the power j omega t, it simply is equal to cos omega t plus j sine omega t. Then e to the power minus j omega t is simply is equal to cos omega t minus j sine omega t. Now if I make a minus here, then I will get e to the power j omega t minus e to the power minus j omega t is equal to 2j sine omega t. So sine 2 omega t is equal to this. So that means you have two exponential functions here. Sine omega t is consist of two exponential functions. One's frequency is positive omega and another's frequency is negative omega, and that's why you get here two spikes, one for positive e to the power j omega t and another is for negative e to the power j omega t. Okay, now let's work with the okay, let me delete all these windows. Now let's make this comment line and activate this line. Now our input, it has been changed. Now our input is a step function. Step functions means you know it, it's u. So I have generated a step function here. Let me run this portion. So it's a step function, right? So it's a step function, starts from here, it's un. So now let's run this cell to find the ACF of the input. So if I try to find the ACF of the input, so this is the ACF of the input, and this ACF looks like this. You have to gain the experience, you have to memorize, or you have to remember that the shape of un, of ACF of un looks like this. So now we have to add a noise. So similarly, if I add a noise here, then let me add a noise. Okay, so if I add a noise, this signal looks like this. I can't understand what was the message signal. Now from this noisy signal I have to extract the message signal. So that's, to do this I have to make an autocorrelation of the noisy signal, and if I run this portion again, I get a spike here. This is for the white noise. This is for actually the white noise. Okay, so this is for the white noise, and you see this part looks like this. So this is the ACF of that un, and this portion quite looks like this. So from this we can have an idea that maybe in this any u function or step function is hidden behind this, hidden inside this noisy signal. And then if I do FFT, then I get a spike at 0. So this is 0 means the DC signal, and yeah, our UN is DC. So DC UN looks like this. So this is UN. So this is even, this is kind of DC, no frequencies present here. And if I run the FFT portion, I will get a spike. So this is my UN, and here you have no frequencies present here, and that's why you get a spike at the 0 frequency. Okay, so by this technique you can detect any signals and find the frequency of their signal using autocorrelation.